thank you very much. So it's been a really wonderful. I think all of us can agree it's been a really energizing and wonderful conference. So I've left myself a note here which I can erase. Let's just start by thanking both the Martins for a really wonderful. I think it's good to do this in the beginning because that way there's no accidental overlap between the legitimate praise for Martins and the illegitimate praise for me. Okay, so of course, thank you also personally for the invitation. I've known Martin for a long time, Martin Ulrich for a long time, and so it's always a pleasure to be able to speak when he organizes something. So I'll tell you today a sort of ongoing story. So it's about an object. I'm going to try and construct an object for you that we're calling the logarithmic Hilbert scheme. So the story, sort of the part I'll tell, will be joint work of mine with Devesh Malik. An important part of it is in the PhD thesis of Patrick Kennedy Hunt, who is here, but maybe okay, he's here. I thought he'd skipped the talk. And also some forthcoming work of Patrick and myself. So the motivating question, let's just start there. Motivating question is the following. So to set it up, let's start with a kind of, okay, we'll start with an SNC degeneration of a smooth projective variety over a curve. Over a curve. So let me just draw a cartoon of that. So if I have a curve, I have some kind of nice smooth general fiber, and then in the special fiber, I'm going to have a single kind of critical value, and in the special fiber, I'm going to have something SNC. So this is going to be some transverse union of smooth hypersurfaces in a smooth total space. Okay, so this is a flattened proper family with smooth total space and a transverse union of hypersurfaces in the special fiber. I'll call the special fiber X naught, and maybe just because it'll come up repeatedly, I'll use YIs to denote the components of the special fiber. So I've drawn three. Of course, there could be many. There could be many components. Okay, and then just also because this terminology will be useful later, let's just notice each component, each YI, it really comes to you as a pair. It comes with a natural divisor, natural simple normal crossing divisor, and sort of this piece. Okay, so this is my YI. So if I just imagine normalizing the special fiber, it comes with the intersections with the remaining components. So maybe I can use some color. So I'm talking about the sort of double the locus of intersections with the other irreducible components. And so I'll often refer to this as a pair. So this would be a smooth projective variety together with a natural normal crossing boundary. So think of the boundary, this divisor by boundary of Y. This is just so we can kind of talk. Okay, so that's the setup, and the kind of motivating question is the following. So let's say I have M of X eta. We consider M of X eta, which is some moduli space of things, moduli space attached to the smooth projective general fiber. This general fiber, what is the right thing? What does that mean? What is the right thing to place in the special fiber? So you imagine this family of smooth projective varieties. Okay, so attached to every point, let's say over this curve, maybe you can think of some moduli space. I'll be more specific in a moment. You can think of some moduli space that might be attached to this general fiber. And the question is, when X becomes singular, when it becomes this reducible union, this transverse reducible union of hypersurfaces in the total space, what is the correct thing, whatever that means, to put in the special fiber of the family? That's the question I'd like to understand, and that's the question that this sort of proposal of the log Hilbert scheme is meant to be an algorithm. Okay? So for today, I'll focus on the case where m of x eta is our beloved Hilbert scheme of that background. I've had 4 days to view other people doing this properly, so extra embarrassing when I do that. Okay, so I'll focus today on the Hilbert scheme. So when I say Hilbert scheme, I mean, we'll fix the Hilbert polynomial, and I won't over decorate the notation with that. Almost everything I'll say today works perfectly well for the quad scheme. There's a version for the moduli space of stable maps, which I will actually mention later on. This is a question that has some long history. Okay, so probably the earliest instance of the question goes back to Gieseker's study of what happens to the moduli space of vector bundles on a curve as the curve degenerates. Okay, but okay, we'll focus on the Hilbert scheme. And maybe the first question to ask yourself, if you've never thought about something like this before, is what's wrong with just the Hilbert scheme? Hilbert scheme. And that's a perfectly reasonable question. So Goethe's construction of the Hilbert scheme works perfectly well for any. Okay. So the Hilbert scheme is the moduli space of subschemes with given Hilbert polynomial, and it works perfectly well when the input into that construction is any variety, any projective variety. It doesn't necessarily have to be smooth, but nevertheless, I'm going to try and convince you that this is probably the wrong thing to do when you have a singular variety of this form. Okay, so the upshot is that the Hilbert scheme of this reducible singular thing is just too big. Okay, so that's the upshot. Let me give you a sense for why. So there are too many subschemes in X naught that have nothing to do with the general fiber. With subschemes in X. Okay, so when you look at that degeneration up there, you're imagining that the correct thing to do in the special fiber is to think about those subschemes that okay, ideally would smooth to the general fiber, but at least in the very basic case that they have some chance of smoothing to the general fiber, and that's actually the property that fails. Okay, so I'll just give you an example. So let's just let me just simplify the picture. Maybe I'll just leave. Okay, I have the picture. So maybe I'll. Okay. So suppose I have. Let's just think about curves. If we're seeing a curve. So let me imagine a curve that just sits in exactly one component with no interaction with the other component. Okay? So when I say this, okay, so this is my subscheme Z. So Z is entirely contained inside one of these yi's. I guess it was y1 and okay, y3 in my picture. So it's just entirely contained inside this yi. And let's say that okay, so that's a perfectly good that's sort of a piece of the Hilbert scheme of the component sitting inside the Hilbert scheme of X naught, right, for some appropriate Hilbert polynomial. And a subscheme of this type has no chance. Okay, this will never smooth out. Okay, so the Hilbert scheme is a complicated object, and so things may or may not smooth out for global geometric reasons. But this is something that I can tell you independent of whatever X might be, whatever yi might be, whatever that. Just the fact that this sits only in one component means that this has no chance of smoothing. Okay, so that already tells you that whatever this Hilbert scheme of X naught is, it's going to be very, very large. It's going to have basically the contributions of the Hilbert schemes of all of the components sort of willy-nilly without reference to what's going to happen in the set. Okay, so the conclusion here is that it's too big. So maybe just to say something slightly more precise, let's say we had say our X naught, just to draw a simpler picture, just consisted of two components, y1 and y2, meeting transversely along something with dimension 1 in each. Then let's say I had a curve in each component. Then I can look at, maybe I'll call this person y12. let's say I have a curve in each component, then a curve of this kind is only going to have a chance of smoothing out if the curve on each side induces the same subscheme on the intersection. So this is something called a predeformability condition. So it's a condition that says basically that whatever this, I call this Z1 and Z2, that Zi kind of is the intersection of each Zi with the Y12 has to be the same on both sides. Okay, so there's some kind of matching condition that has to be taken into account. Yeah. Yeah. No. Okay. So yeah, that's a great question. So firstly, if I really have a smooth proper curve, the Hilbert scheme, even in the smooth locus, they're probably not going to be, right? But if in fact, even worse than that, there's no chance of really figuring, if I take the flat limit, even if, let's say, it was smooth in the general fiber, let's say it was irreducible or something in the general fiber, that taking that flat limit is nothing we're ever going to be able to describe. So yeah, so this is why I'm being a little bit careful about what I'm saying. I'm definitely not saying I want to study those subschemes that come from the general fiber, but I want to study those subschemes that sort of independently of the global geometry have some chance of coming from the general. So the answer will justify the Okay, so another hope that you could have is to have an alternative. Yeah. Yeah, so I mean, yeah, we can talk. Yeah, sure. So the point is that once you put this special fiber inside the total space, it's like a Cartier divisor inside the total space, and that special fiber is just like a principal fiber, right? And so that imposes some intersection theory, just imposes some relation on what the different intersections could be with the subscheme. Okay, so this just gives a contradiction. There's a numerical contradiction that comes up. If it's smooth, then you could do intersection theory on the total space, and you can see that. Yeah. That requires a little bit more things. Maybe let's talk again. It's a small calculation. Okay. Any other questions? Okay. So the other hope that you might have if you were thinking about a problem like this is that you might want whatever shows up in this, in this alternative universe, whatever is going to live over 0 in the corresponding family of Hilbert schemes. You might hope to have an alternative field such that, okay, so that can be described. In terms of field of the y. So if I just practically said, please construct a subscheme of x naught, the way you're probably going to do it is you're going to take out the pieces of x naught. You're going to build, going to write equations to cut out a subscheme in every one, and then sort of try to stick them together. So not every subscheme can be, not every point in Hilbert x naught can be described in. So this hope fails. Okay, so there are reasons. The reasons for me come from enumerative geometry. Why this is really something quite desirable. So we would like to study the properties of the Hilbert scheme of a smooth projective variety by degenerating into a union of simpler varieties. This is kind of standard technique in enumerative geometry, and it's not a new one. And for the Hilbert scheme, we currently don't really have something that's. Oh, so that's roughly what I would like to do. Well, at the end, yeah, so that's a theorem. Theorem is the proposal for something that's done. Yeah, so because the Hilbert scheme is kind of a nasty object, it will require some justification of the answer that I'm going to give you for the reason. But okay, so I have no idea what I'm doing. So let me explain the proposal. So I should put some names here. So a version of this proposal is due to Jun Lee and Bao Sen Wu about 15 years ago. And then there's an upgrade of it. I'll explain why, what these different upgrades are in work of David Schmalik and mine from 2020. And then maybe the most complete proposal for this comes from Patrick's PhD thesis. So roughly speaking, what Li Wu did was they studied that special case that I mentioned earlier when the special fiber just consists of two components meeting converse. Okay, so for various reasons, this turns out to be a very special case, but nevertheless, they basically completely solved this problem in that case. So Devesh and I were studying the Hilbert scheme of curves specifically and came up with a proposal in the normal crossing situation, and that proposal was generalized sort of to the quad scheme. Yeah. So the proposal is the following. So we have this Hilbert scheme of X naught, the Hilbert scheme of the singular space, and somehow the claim is that this is bad or too big. But inside of it, just by thinking about small examples like the one that is hiding in the board back here, just by thinking about small examples, you can identify an open subscheme of the Hilbert scheme that behaves well. So I'll call this okay. Just put a circ off. And okay, so let me explain what this is. This is going to be some open subscheme, open subspace of Hilbert law, consisting of basically parameterizing subschemes with a property that I'll explain in a second. And then the idea is, okay, the remaining stuff is not so well behaved and so has to be replaced. And that will be this guy. Okay, so this person is of course compact. This is open in a compact, non-trivial open inside this, so it's going to be non-compact, but this is once again going to be. Okay, so just like many moduli problems, I identify some locus that I'm happy to play with, and then there's some locus that I don't like, so I throw it out and replace it with something more geometric. So that's roughly going to be the story. So let me now explain what this open locus is. So this is kind of a simple thing. So this is the subset of the subspace of the Hilbert scheme that parameterizes those subschemes of X naught that are, so Z is transverse to the singular locus. That's the definition provided. I should tell you what I mean by transverse here. So where transverse is following. Okay, so there's two conditions. If I look at Z intersect yi, okay, so if I look at what my subscheme is going to be on one of these irreducible components, on Z intersect yi, the boundary components, partial yi, they form a regular sequence. On Z intersection. Okay, so in other words, that the boundary sort of the pieces of the boundary intersect completely in the sort of smallest possible subscheme on each Z. Okay, so okay, so that's the first condition. And the second condition is okay. This is not intuitive. How did you guys do this? It moves in the opposite direction. Okay, so so then the second one is a matching condition on yi intersect yj, which is exactly what I said earlier. When you have a subscheme yi and a subscheme in yi and a subscheme in yj, and you look at the intersection yij, the induced subscheme from each side is the same on the double over. Okay, and similarly, and and further and higher addition. Okay, so there's a few different ways to make this condition precise. So one way to say it is that there are no higher tors when you perform the intersections of the zi's with the other irreducible components. That's one way to say it. You can also phrase it as a flatness condition over a certain Artin stack. And okay, there's a few other things. The tor condition is good because it sort of immediately tells you that this is an open subscheme. It's a higher tor vanishing condition, so it tells you that this is going to be an open subscheme of this. Okay. So basically, what have I said so far? It's just that there's this locus. Okay, so this is sort of obviously too big. You run some experiments, and then you find that there's a natural open subset, which is defined by transversality to the singular locus subset. Okay. Yeah, you just have to do everything in tau locus. So I mean, yeah, the regular sequence condition is sort of local on the ZI. There's a version for toroidal intersections as well. Let's leave it. For the ZIs? Yeah, the ZIs can be horrible. This is completely done. The correct definition seems to be just that they form a regular sequence. And there's various reasons why we sort of know that that's the right condition. Okay. Okay, so right. So I can now tell you, having identified somehow the open subset, the kind of interior of the moduli space I'm about to construct, this Hilbert knot defined by transversality conditions of the singular locus, I can tell you what the proposed compact version of this moduli space is. Okay, and the answer is actually quite simple. And I'll do some examples afterwards, so it won't be so mysterious. Okay, so this is Kennedy Hunt. So the proposal is to study a moduli space, some kind of moduli problem, which I'll call log Hilbert of x naught. And what it will be is subschemes not inside x, but inside some birational third degree of x. Okay, where so x naught tilde, so x naught is a blow up, technically blow up for space change. Of x centered in strata of the spectral fiber. I'll draw a picture that will make it a little bit more obvious. This is the first condition. The second condition is that Z is transverse to the transverse in the sense that we discussed above. So everything inside that looks like it should form a regular sequence forms a regular sequence. And then finally, this is sort of the slightly subtle one, that Z inside x naught tilde is minimal, which just means it's not pulled back along a smaller blow. I don't know how. I don't. Yeah, so maybe one way to say this that it's a okay. I can't state it as an ampleness, but I can state it as a finiteness of automorphism. So that's the thing. Okay, but you have to be a little bit careful. This is just as a set. I haven't told you exactly on what this is a moduli functor. This is a moduli functor on the in the category of logarithmic schemes, and in that category it's finite one. Okay. Okay. So let me draw just a couple of pictures so you know what these objects might look like. Let's just go back to our example X naught, which had these three pieces. Okay. And I'm thinking about X naught in its smoothing family that was presented to me from the beginning. And so what the first one says is, well, you can change X naught by blowing up some center in the special fiber. So maybe the simplest thing you could do is you see this big triple intersection here. You could blow that up and you will get a new component. Which sort of is a P2 over the, okay, this is really three surfaces meeting. Then there's a P2 sitting over this triple intersection, and then these get blown up and up. And exceptional components. Two, which is the blow up of the yi. Okay, and then you could keep going with this if you wanted. Okay, so for example, maybe you could pick this, you could blow that up, and I'm not sure I want to draw that, but okay. I'm not sure. Okay, introduce some kind of bubble like there. Okay, where this is your blow up of your P2 at a point. This is some kind of P1 bundle. These are the quick transforms of the y's. Okay, so let me just emphasize one thing. There's a lot of these, right? Because I can blow up any stratum, and then I have more strata, in fact, and I can blow those up, and I can keep going and keep going and keep going. And so in principle, the possible X naught, okay, there's something about reduciveness of the special fiber, which let's all just ignore. If you see it, you probably know how to fix it. Okay, so the possible X naught tildes are some huge infinite list that I, in principle, can't think of. This is some very large list. But okay, granting that those X naught tildes are what's allowed, you know how to put a subscheme in. You just build a subscheme in each of these yi's that are transverse in the sense that I said. So they have this regular sequence property, and they match whenever components in it. Okay. So in principle, this is a kind of simple. Any given object is simple. You could really build one. It's not hard to actually build one. So the fact that there are so many of these is why this third condition is important. Okay, so now I will say a little bit about what we know about this guy. Any questions about the definition? I'm being okay. I'm sort of leaving out the log geometry, even though this has log geometry in the title. But yeah. Yeah, no, not quite. There's some kind of equivalence. Yeah, so this last condition is putting an equivalence relation on that. So it's saying that when there's supposed to be a smallest one, and so that's I'll say that there's supposed to be a smallest one, and so everything in that colimit is going to be equivalent to that. So yeah, the thing you described is probably not going to be bounded, but the moduli problem I will describe is funny. Any other comments? While I make a fool of myself. Okay, so there's two theorems about this that I want to state, and then I want to switch and just show you some examples. I'm introducing an object that looks a bit unwieldy, so I at least want to convince you that maybe you already care about it. Yeah, I'm coming. That's of course, yeah, it's a good question. I'll come to this next. So that's literally the next theorem. Okay, so I think this theorem might test your patience, but it is what it is. Okay, so there's a theorem here. So this has to do with the condition 3 that I mentioned above. So given Z inside X naught tilde inside, mapping to X naught, transfer subscheme. Okay, maybe I'm sorry. Let me put a prime here. There exists a minimal X naught tilde, which receives a map from X naught tilde prime. And sorry, let me put a prime there as well. And the subscheme Z inside X naught tilde such that if star there, such that the natural pullback diagram commutes. So Z lives inside X naught tilde prime, X naught tilde Z. So that's the first, minimal, Okay, but there's a star here, so don't get too excited. So, okay, but what is the theorem saying to first approximation? It's saying that let's say you did this, right? You went through the procedure that I told you to build an object of one of these log Hilbert schemes. So you blow the hell out of this X naught. We put some subschemes in every single one. Then I'm saying that we can give you a procedure that says that there is a blowdown of that ambient, a canonical blowdown of that ambient, and the subscheme inside that canonical blowdown transfer. Implied such that the thing that you built is a pullback of a minimal guide. Done. Okay. So the content of this is it says that, okay, so the moral conclusion here is that log Hill has some chance of being controlled. Okay, so it's not too big. So that's the sense in which it's important. Okay, so let's explain this caveat. Okay, so exists as what? Okay, so this only exists as what's called the logarithmic algebraic space. But it's an hour-long talk, and it's the last day of the conference, and it's the last talk and the last day of the conference. So maybe just don't worry about it. It's basically a scheme. It's basically a scheme. We've been working, people in log geometry have been working with this for like 5 or 10 years now. It's all fine. Okay, you can work with this basically like you can work with the scheme. Just take, I wouldn't lie to you. I wouldn't. We're friends. I wouldn't lie. Yeah. Yeah, the same statement in table maps case and for plot schemes and all of that. That's great. It's not an algebraic space. Okay, so I could, okay, maybe I'll say one more word. So in log geometry, there is some class of morphisms that are called log étale. So this is basically where you change all the definitions of étale, but you throw the word log in. Okay, so a typical example of something that's log étale is a blow up at a strap. Okay, that's something that's log étale. But that forms that give or take forms a topology, some kind of Grothendieck topology. And you can quotient by log étale equivalence relations. You can quotient schemes by log étale equivalence relations, just like you can for. So this is not any further from schemes than sort of algebraic spaces are. For those of you who are not log people but have seen a little bit of Berkovich analytic geometry or rigid geometry, it's very similar to objects like the tape curve or the uniformization of maximally degenerate abelian varieties. That it sort of has that kind of flavor. Okay, but trust me, it's really fun. It's really fun. Yeah, there's a few different ways to present it. It's common. It differs from a scheme only by combinatoire. Maybe that's the simplest thing. Okay, and then theorem. Okay. Log Hill X naught exists with the same caveat. Okay. And moreover, is proper. So it exists and is proper. So what proper just means is that it's sort of finite type in appropriate sense for spaces of this kind, and it satisfies the value of the criterion. Maybe the last thing I'll say, furthermore, The closed immersion is closed immersion, again, in this funny world that goes from log tilde of x naught into the product of log tilde of each yi relative to its natural bound. Okay, so let me say a word about this. So this is fulfilling the hopes that I outlined earlier, that you would want the objects in the special fiber to be described by subschemes in the pieces that have been stuck together. So this is fulfilling that hope. I've chosen to explain this construction for a degeneration, but everything I say works perfectly well for a pair as well. Okay, so just like there's a log tilde of a special fiber, there's also a log tilde of the individual components of the special fiber, and it works exactly the same. Okay, so whenever you see a regular sequence, or whenever you see something that looks like it should form a regular sequence, it's a better form of sequence. Okay, so those are the two theorems. This one, okay, the second one needs the first one, but I think it's interesting in its own right. So, okay. Yeah, so the reason you need the minimality is because if you did that, it becomes very hard to show boundedness. So here's the issue. One point at a time, maybe you can say that anything that's pulled back along blow up is equivalent. But in a family, you need to know that you can do those blow ups uniform over a higher number. So all of the juice here really comes when you're working over a higher number. Yeah.
So in a log algebra, can you do the same like in your mental count so that you can do like that or like?
Yes, you have to make a choice, and the choice never matters. And yeah, I'll explain. Yeah, there's some things that have to be that we choose to do that. Okay, so that's the sort of technical part. The part I would like to share now. So this theory comes with a lot of kind of, I think, quite tricky examples. I'd like to show you something. Examples. Okay, so I'm going to show you a couple of examples, one from higher dimensional geometry and one from enumerative. So maybe since I let it go by a little bit quickly, let me just emphasize just the following. So log tilde of, let's say, yi relative to the boundary of yi, let's say y relative to the boundary of y, I'm showing SMC pair. Is defined similarly. Okay, so what I mean by that is that if you have a variety with some kind of divisor, y, then again, you can name some interesting class of subschemes by, for example, okay, in this case, you have to do deformation to the normal cone. So, for example, you can do this thing that people like to call bubbling. So you can put y in a one-parameter family and blow up this kind of squiggly divisor several times, and you sort of produce something reducible, and then you study subschemes. Okay, so these are allowable objects, and then everything I said works absolutely the same. Okay, so you have to impose a minimality condition, and okay. So what are some examples that you can play with? And I hope this will maybe convince you that this is interesting. The first one is sort of a link to KSDA moduli. So let's consider pairs. Consider pairs of the form Pn comma H, where H is the transverse union of let's say at least n plus 2 hyperplanes. Picture, there's everyone's favorite picture of Pn. I add in some lines. So I table. And so following on from what Phil told us, there is a moduli space, allegedly, of KSDA stable pairs. And we can look at the locus in the moduli space of pairs of this form. So this is log general type, right? Because this is the log general type condition. And so we can look at pairs of this form and then look at the associated KSDA moduli space with these numerical data. Okay? So I want to tell you how the log Hilbert scheme plays into this. This is maybe one of the simplest examples of a KSDA on. Okay? I want to explain the log Hilbert connection here. Well, remember the KSDA moduli space is about abstract varieties. Hilbert schemes are about embedded subschemes. Nevertheless, here's something you can do. So if you take Pn minus H, this is a non-compact variety. And because I've deleted a large number of lines, at least n plus 1 line, this subvariety, this non-compact variety admits a very large number of invertible functions. Okay? There's lots and lots of maps to C star. In fact, so many maps that, and a large number, so many maps that I have to use a capital letter, and also so many maps that it actually embeds the sub. Okay? This is not so hard to imagine, right? So if I suppose P1, and I delete 2 points, there's a non-trivial map to C star. If I delete 3 points, there's a non-trivial map to C star squared by embedding the line as a generic line inside P2 and then deleting the boundary and so on. Okay. So then just by a little bit of kind of basic toric geometry, this thing you can view as a subscheme of some toric variety. Right? So I mean, basically, this is just Pn embedded inside this toric right? Right? And so now, because so this is a pair. So now we can consider log Hilbert of the pair Pn and with the coordinate value. So just by taking an, because this embedding is canonical. Okay, I don't know why I chose to delete the H. I think there was something else in my head, and this is not transferred. In any case, I can view a Pn together with a bunch of hyperplanes as being canonically a linear subspace of some other projection. Perfectly legal thing to do. And because of that, every KSDA stable pair determines a point in the log Hilbert, okay? Because it's a subscheme of a pair. And so this construction will output some class of generation. No, yeah, it's a beautiful coincidence that in this fact and in this geometry and a few other geometries, it's not a log algebraic. So that has to do with the fact that we're doing something linear. So I think there's some people in the audience who know things about matroids. So the fact that it's, yeah, we're coming to that. Yeah, so that's an example. The wonderful compactification gives you, so the wonderful compactification is for a hyperplane arrangement complement can be viewed as a subscheme of a pair where the pair is just a toric variety with its toric pair. So this is completely compatible with that. Okay, so what's the fact? Log Hilbert of Pn coordinate boundary of P capital N where the boundary is P capital N. It's the KSDA moduli space of pairs P little n comma H. It's horrible notation. Numerical data. Right hand side is proper, the left hand side is proper, and this map is an isomorphism on physics properties. I have to put rubber here. So whatever the KSDA moduli space, okay, this is the simplest KSDA moduli space. But the fact that Pn relative to a bunch of hyperplanes, the hyperplane arrangement canonically embeds, just by virtue of the boundary, you get the equation from the divisor. The fact that it canonically embeds inside of a projective space means that you can view that as a closed subscheme of a logarithmic scheme, thereby determining a point of the log Hilbert scheme. And so our construction constructs some kind of moduli space here, and there's an isomorphism onto the corresponding KSDA. Okay, so this is, I should say, this is, I don't want to phrase this as a theorem because really it's just identifying that what we do reduces to earlier work, packing, Thiel, and Pevelet. Yep. Yeah. Yeah. Okay, so maybe for time, I won't give too much about the other example, but another, you have to match the degeneration. You need to know that the degenerations that appear in the log Hilbert scheme are actually KSDA stable. And so you have to think about it. Yeah, so maybe the simplest way to think about it is via a theorem of Thiel and Pevelet. You can think about this as a certain Chow quotient, and then that Chow quotient is sort of explicit enough that you can just name an isomorphism. Okay, so another game that you can play that's very similar, I won't give the details on this, similar and equally fun, is that if I take a cubic surface, that comes with its own set of very interesting lines, namely the -1, the set of all -1 to 27. So that's a pair. And if you take a cubic surface and you delete the 27 lines, that again embeds into some toric variety in this fashion. If you delete the 27 lines, that a cubic surface now admits lots and lots of invertible functions, enough to embed the complement of the 27 lines into an algebraic torus. You can close up the cubic surface inside that algebraic torus in such a way that this is transverse and therefore defines an element of the logarithmic limit. So similarly, this is again basically relying on a different paper of theirs, log Hilb cubic surfaces. So it's equal to the stable pair. Okay, so these are even nicer. The space of hyperplane arrangements is kind of a nasty moduli space. It had lots of irreducible components, and it's non-equidimensional, and all that kind of stuff. This is a beautiful space. The space of cubic surfaces is smooth and irreducible with normal crossing boundary, and we can view it as an instance of the log. Okay, so that's kind of application to higher dimensional geometry. When it's so okay, I should, yeah, maybe let me take the opportunity to say these are accidents. So let's say you took KSDA stable pairs with P2 and a bunch of higher degree terms. I don't think it will coincide with the log Hilbert scheme anymore, but maybe it gives you some avenue of action. So maybe there's a map, or maybe there's a sequence of rational maps, like in this wall crossing picture, that takes you from here to the KSDA. But in small examples, this seems to be a nice way to think about it. Yeah. Yes. Canonical up to, so I put this rubber here, canonical up to C star to the end. So you can do this on any algebraic variety. Take any algebraic variety, you can take O star, that's just, and you can mod out by K star. That's the finitely generated abelian group, usually trivial. In these cases, it happens not to be trivial, so so non-trivial that it embeds inside an algebraic torus, and so it converts a problem about abstract varieties into a problem about embedded varieties. Yeah. That's right. Okay, so in my remaining 10 minutes, I get to talk about the thing I got started on this direction phi. So this is the LMNOP correspondence. Okay, so let me just give a brief reminder of how this story goes. Okay, so if X is a smooth projective threefold, the MNOP, the usual MNOP correspondence for the Gromov-Witten DT correspondence, is a proposal for conjecture relating two sets of invariants. Relating two sets of invariants associated to X. Sorry, Molech, Microsoft, OpenCoff, and Rahul. L is log. If that's not clear. Okay. So the first part of the proposal is Gromov-Witten theory. So in Gromov-Witten theory, you start off with a smooth, so there's no log anything yet. So this is just a smooth projective threefold. And you build from this threefold the moduli space of stable maps to X in some curved class beta. So this is some moduli space that basically that is basically concerned with genus G curves in X of living in a fixed homology class. And then by some kind of integration theory, you extract what's called the Gromov-Witten partition function. So this is some power series whose coefficient count in this kind of funny Gromov-Witten sense, they count stable maps. Didn't budget the forward moving time. Okay, good. Okay. So that's Gromov-Witten theory. The second proposal is DT theory. So here one starts with X and builds what at least traditionally was called IN X beta. So this is the Hilbert scheme of curves with X with class beta subschemes with class beta and holomorphic Euler characteristic n, right? So just exactly parallel to the genus and curve class parameter upstairs. And again, there's some kind of fancy integration theory that produces the DT partition function. Okay. And so what is the MNOP conjecture? It's that after appropriate normalization okay. So after you appropriately normalize, you can remove some term, but after you appropriately normalize this and change variables, this basically becomes equal to the Gromov-Witten. Okay. So this is kind of a highly non-obvious statement. It's known in many cases. Maybe quite spectacularly recently, it's known for a large class of varieties in what's called the primary case, without descendants, for those of you who think about these things. Okay, so let me state a theorem. All right, don't worry, this is not going to be a proof of the MNOP conjecture. You can stop writing. Okay, So let's say x to b is an SNC degeneration as previously. Okay, so there's a formulation of we're going to put in MNLP for pairs, for the pairs yi partial y, right? And the theorem is that this version for pairs, okay, it's going to be called LMNOP or log MNOP, LMNOP for all the yi's with respect to the appropriate boundaries implies the MNOP conjecture for the general. Okay, so what this statement is saying, so this, I should say, this is maybe it's important to note in the subject, this is sort of with all the bells and whistles, so with descendants and primitive cohomology and all of that stuff. So this is really a completely general statement. It says that when you have an SNC degeneration, there's a kind of relatively straightforward formulation, an extension of the MNOP correspondence to pairs, where the input is no longer a smooth projective variety, but a smooth projective variety together with a boundary divisor, just like in the special fiber of those families that showed up right at the beginning of the talk. Let's call that the LMNOP correspondence. And the theorem, the content of the theorem is that the LMNOP correspondence for these pairs, all these pairs in the special fiber, implies the conjecture in the general. Okay, so why might we care about this? In your head, you should think that X eta is some variety that you picked up off the street and has no good properties whatsoever besides being smooth and projective, whereas the special fiber has a good chance of being something with a lot of structure. Maybe it's a toric variety, maybe it has, maybe it's rational at least. So for example, all Fano threefolds are expected to admit generations of that kind. And we have some feeling that the conjecture is much easier to prove in that context. Okay, so how is it proved? Well, the logarithmic Hilbert scheme for a threefold admits a virtual fundamental class, and that virtual fundamental class, just because, in the way that I said in the beginning, that the Hilbert scheme of the special fiber injects, in some sense, as a closed immersion into the product of Hilbert schemes. Because of that, one can write down formulas that relate the enumerative geometry of the special fiber in terms of its components. Okay, and the theory just tells you that that's connected to this. Yes, this is with the vanishing cycles. Okay, so I hope that at least convinces you that this log Hilbert scheme has some good properties. We can actually work with it, and there's a few good examples to play with. And other than that, just I should thank you for your